So the course is research oriented. The course is research oriented. So I will be taking you on aspects of gravitational physics, specifically on general relativity and applications to astrophysics. So the next slide, please. So it's not a foundation course, it's a research-oriented course. So we're building on what has been done already. But we'll take some time to recap some of the things for those who are not there during the foundation course and those who are attending for the first time. So our building blocks, as I've said earlier, the first one is the foundation course that we had some years back. I'm happy I've seen some faces that attended that foundation course. So you are going to help others to pick up as soon as possible. So we'll review some basic concepts of relativistic astrophysics. Then we'll try to look at some research questions on spherical plasma stars. Okay, I've chosen this so that we can have some work to do. From there, once you leave this place, you can expand it and do other things. So we'll start with a quick recap of general relativity. As we all know, general relativity is a theory of gravitation. We have other theories of gravitation like Newton's theory and then many others that are not as familiar. So general relativity is built on two major concepts, what we call the strong equivalence principle and what we call the lift G-Dunking. And as we know, general relativity was formulated by Albert Einstein after formulating his theory of special relativity. Okay? And general relativity came about because there were some aspects of Newtonian gravitational theory that could not be explained. So Einstein thought it wise to see if he could do that. And the issue started with Maxwell's equations. When Maxwell's equations came on board, Einstein thought that he could also formulate gravitation the same way electromagnetism is formulated, using Maxwell's equations. But he tried that and it failed. So he said gravitation should be a force with a difference. We can all recall that there are four fundamental forces in nature. We have, who can name them? The first one, gravitational force. Second, electromagnetic force. Third, the strong force or the nuclear force, and the electroweak forces. Okay? So Einstein discovered that gravitation is unique because it could not fit the same way electromagnetism fitted in Maxwell's equations. So he started thinking out of the box. And he looked at what we call the strong equivalence principle. In the strong equivalence principle, he first of all appreciated acceleration in a magnetic field. An acceleration in a magnetic field is given as that. Okay. So you can easily see that acceleration is inversely proportional to mass in an electromagnetic field. Are we together? Acceleration is inversely proportional to mass. this is in an EM field. But when you now come to a gravitational field, you will discover that the acceleration okay, this is G. You discover that the acceleration does not depend on the mass. And why is acceleration not depending on mass? Because of this. And what is MP? What is MI? MP is what we call the passive mass. And this is what we call the initial mass. Initial mass. So the strong equivalence principle states that this passive mass is equal to the initial mass. And there were experiments that were performed to ascertain this equality. So because of that, the acceleration in the gravitational field does not depend on mass. So if the acceleration in the gravitational field does not depend on mass, and the acceleration in the electromagnetic field depends on mass, then these two fields cannot be they are unique, so to say. So this was the first point that Einstein brought about. That because this acceleration does not depend on mass, and this one depends on mass, then gravitation needs a different approach. Secondly, he looked at this experiment, the lift Gedanken. Gedanken is just experiment in German. You can call it the lift experiment. Okay, lift Gedanken. And in that experiment, we have somebody maybe in an object that is falling freely, okay, to the Earth's surface. We have somebody, and the person projects a projectile. He throws something like a stone. Okay? And the person is in free fall. He's falling down under gravity. And then he throws a stone. Okay? So, if we assume that there is no air resistance, then this person will see this stone moving in a straight line. He will actually see the stone. The stone will move in a straight line, and then the stone will start moving down at the same speed with him. Do you get the point? The stone will be moving at the same speed with him until he gets to the ground. But if somebody is outside here, he will see the stone defining something like what? A parabola. It will move in a parabolic path. But for somebody inside here, the stone does not describe this type of motion. So, to the person inside here, gravity is not acting on the stone. It's as if the stone is just standing and he too is standing. Okay, although they are moving downwards. It's as if gravity is not acting on the stone. So he sees the stone stationary and himself stationary. And both of them are moving down. But to the person somewhere here, he sees the stone describing a parabolic path. So Einstein said that this is a local coordinate. That in a gravitational field, it's possible to pick out a local coordinate where gravity seems not to act. Do you get the point? Because to the person inside here, gravity does not seem to act. So it's possible to pick a local coordinate system where gravity does not act. But in electromagnetism, you cannot isolate part of an electromagnetic field where the electric force is not acting. Do you get the point? In an electromagnetic field, the electric field acts everywhere. But in a gravitational field, we are now seeing a local coordinate system where gravity seems not to act. So gravity is different from electromagnetism because we can have such a coordinate system. Are we together? So these are the 2 points that gave birth to general relativity. These are the 2 points that gave birth to general relativity. And actually, this experiment is a thought experiment. It's a thought experiment. And we know what I mean by a thought experiment. It was not performed in any laboratory. Okay, it's a thought experiment. The next slide, please. Okay. Any questions so far? Any questions so far? I expected you to ask me this question, and you didn't. So I'll ask you tomorrow. What is passive mass? What is initial mass? So please, I'll ask you that question tomorrow. Actually, there are 3 types of mass. There is what we call active mass. There is passive mass. And there is initial mass. So initial mass is the mass of an object in an electromagnetic field. Passive mass is the mass of an object acted upon by a gravitational field. An active mass is a gravity generating mass. This is the simple definition I can give you for now.
Sorry, sir. Why the assumption of the fact that passive is the second definition? Why? Because based on the definition that you wrote that.
Yes.
That is the passive is the second definition.
That is it. That is it. The mass.
Okay, I just give you a
It's okay, bro.
Space constitutes what? Gas. Yeah, gaseous in nature. And then having an electromagnetic field in question, we try to see how this mass you have. You have the neutron mass, you have the proton mass, you have the ion. So you have ion, proton, electron. But when the electron is a little bit passive, because what is happening here is the neutron and the proton. At that level, because of the high temperature that's involved, we have what is known as quasi-neutrality. In that case, the masses are equal. And when you infuse, because the gravity, actually, when you look at G, at that level, is a little bit low. When you try to pacify that with the speed of light, under the quasi-neutrality, the passive mass, or what you call your initial mass, will be the same. You don't differentiate them.
Okay, so let's make progress. Actually, there was an experiment performed by this guy to show that MP is the same as MI. So let's look at what we call a metric tensor. A metric tensor. Okay. What I didn't tell you initially is that general relativity is a geometrical theory of gravitation. It's a geometrical theory of gravitation. Okay, while Newtonian theory is a dynamical theory. Okay, Newtonian theory is dynamical. Einstein's theory is geometrical. Okay, in Newtonian theory, you have a force and a potential. Okay, you have a force and a potential. But in Einstein's theory of gravity, you have what we call tensors. Okay, we use tensors. We use tensors. Use tensors. I hope you are familiar with tensors. You are familiar with tensors? Okay, because there's a course at undergraduate tensor analysis. Though some universities are not offering it again. Okay. So what we are going to be saying is based on tensors. On tensors. I gave my notes for the last course so that it will be shared to you. You can take time and go through it so that you can revise some of the things. And those who are not familiar with them, you can pick some aspects from there, then we can always make progress. Can always make progress, because if we take all the time talking about this, we are going to end up with a foundation course and not a research and not a research-oriented course, and the idea will be defeated. Okay, so we expect that we'll not only end with the lectures. After the lectures, you have a lot of work to do. A lot of work to do. Okay, after the lectures, when we are coming the next day, we expect to see much progress. So you are not coming here to relax. We are coming here to work. And at the end of the day, we'll go back with one thing or the other. So please, if there are any concepts that you don't understand, when we go back, you read on them, and the next day you ask questions, and so on, so that we can make reasonable progress. So I expect that I'll give you a recap of general relativity between today and tomorrow. Maximum next tomorrow. Then after that, we will now try to look at research questions. Okay, we'll look at some research questions, and then we try to see how we get solutions to them. Okay, so special relativity is Einstein's theory of electromagnetism. Okay, and the line element in special relativity is of this form. Okay. It's of this form. Okay. So this is a tensor of rank 2. This is a tensor of rank 2. So in essence, what I'm saying is that this can take values from, if you decide to start from 0, you end at 3. This one same. So if you permute these two, you are going to get 16 components. Okay, you're going to get 0, 0, 0, 1, 0, 2, 0, 3. Okay, 1, 0, 1, 1, 1, 2, 1, 3, 2, 0, 2, 1, 2, 2, 2, 3, 3, 0, 3, 1, 3, 2, 3, 3. So you are going to get something like this. Okay? You are going to get something like that. So in essence, this has 16 components. It has 16 components. Okay? It has 16 components. And the difference between that of general relativity and special relativity is just the G. Is the G. And actually the G is what carries the information about the gravitational field. If you remember your classical mechanics very well, you will recall that once you have the potential, you can get all the information about the field. Is that not? Once you have the potential, you can get the force. Okay? You can get the force. And you can get other parameters. Once you have the force, you can get the acceleration. Okay? You can get the velocity. And so on and so forth. So once you have the potential, you can get the force and you can get other things. But in general relativity, the building block is the metric tensor. The metric tensor is the building block. And we are going to see how useful the metric tensor is. How useful the metric tensor is. So as I said earlier, please collect the notes and try to read a bit about tensors if you have forgotten, so that we can move a bit faster. A bit faster. So like what I've said here, I've said the fundamental quantity in general relativity is the metric tensor. Unlike the potential in Newtonian theory. So once you get the metric tensor, you are as good. You can relax and take a cup of water. You are as good. You can go. Once you have the metric tensor, any other thing about the gravitational field, you will get it. You will get it. So what we are going to do a bit later is that we already have a metric tensor. So we are going to use that metric tensor to try and see what we can do with it. And we are going to appreciate what I'm calling a spherical plasma star. A spherical plasma star. So we'll use the metric tensor we have and try to appreciate the gravity around that star. We'll appreciate the gravity around that star. We'll try to look at the equations of motion of particles around the star. We'll try to look at the way a photon behaves around that star. We'll try to get the field equations around that star. We'll try to study some gravitational phenomena around that star. Something like gravitational time dilation, gravitational length contraction, gravitational spectral shift, and many other phenomena. So that's what we are going to do. And it's going to be an interesting exercise. Any questions so far? I want us to flow. Any questions so far? Am I speaking to myself? Because it's possible I can be speaking to myself. Okay. I used to have students that when you are lecturing, they are nodding their head. And at the end of the day, they score 0. You begin to wonder why were they nodding their head while you were lecturing. So if you don't understand anything, please, feel free. Feel free. I don't want you to go back the same. Okay? You have to go back with something. That's why you are here. I'm sure my Ogade will have told you that so many people applied for this course. And you are the few that we are choosing. Okay? So we expect that at the end of the day, this course should be productive. Very, very productive. We should achieve a lot. Yes. Yes. Okay. Yes. You know a vector has how many components? 3 components. You have I, J, K. These are space components. You can add a time component to make it 4. Okay? So we call a vector to an extent is a tensor of rank 1. It's a tensor of rank 1 because it has just 4 components. So if you want to write it, you can decide to write it like this. Then I can have T1, T0, T1, T2, T3. So you see it has just 4 components. So it's and this one is, we call this a contravariant tensor. There is also what we call a covariant tensor. When this index is here, when you have this, it becomes covariant. When it is up here, it is contravariant. Okay? And then there are situations where you can raise the index or lower it. You can raise the index or lower the index. So as I said, please, you collect the notes and go through them. I don't want us to go into the intricacies of raising tensors, lowering tensors, defining tensors, and so on. But once you go through a note and there is any question, I will readily answer so that you can be able to flow. Okay? So this is a tensor of rank 1. There's also a tensor of rank 0. A tensor of rank 0 is a scalar quantity. A scalar quantity is a tensor of rank 0. A vector is a tensor of rank 1. And then when you go beyond that, you have a tensor of rank 2. You have a tensor of rank 3. Actually, we are going to see tensors of rank 4. What we call the Riemann-Christoffel tensor. Okay. it's like this. So we are going to see this tensor along the way. It's what we call the Riemann-Christoffel tensor. It's a tensor of rank 4. So how many components do you expect it to have? How many components do you expect it to have? How many components? A tensor of rank 3 will have 64 components. Then a tensor of rank 4 will have how many components? 200 and? Okay, so a tensor of rank 3 has 64 components. So 256. We are going to have 256. Okay, we are going to have 256 components of this tensor. Okay, so we are going to meet. This is the highest tensor we are going to meet. Yes. This is the highest we are going to meet during this course. We will not go beyond. We will not go beyond 4. Okay. We will not go beyond 4. Any other question, please? Any other question? Okay. The next slide. Who can identify the first equation? Is? Okay. So that's Newton's gravitational equation. Gravitational field equation. Newton's gravitational field equation. So that's the equation that describes the gravitational field using Newton's theory of gravitation. Okay. What is phi? Gravitational scalar potential. What about G? What about rho? What about rho? Yeah, it's density of mass. It's density of it's mass density. Okay. So I always bring in Newtonian so that we compare with general relativity. Okay. So that is Newton's gravitational field equation. And from that field equation, once you get the gravitational scalar potential, you can get all the information you require about the gravitational field. Okay? But in Einstein's theory of gravitation, we are going to meet a different set of equations. Okay? I remember during the foundation course, we took time to derive all these equations. The first equation is what we call the geodesic equation of motion. Geodesic equation of motion. Okay? One thing I did not say is that gravity curves space. Without gravity, space is flat. With gravity, space is curved. Okay, that's why you call the line element in special relativity the flat metric space. And that in general relativity is a curved metric space. Okay, so in general relativity, particles move along what we call geodesics. They move along what we call geodesics. They don't move in straight lines per se, because they move along. A straight line will only be possible in the case where gravity is absent. So they move along what we call geodesics. And this is the geodesic equation of motion. Did I type this equation correctly? This is supposed to be x. X to the power v, x to the power alpha also. Didn't type it correctly. It looks beautiful. The equation looks beautiful. Okay, so this is what we call the geodesic equation of motion. And remember, I told you that once you see these indices, alpha, beta, gamma, or any letter, they are running from 0 to 3. Okay, and in this case, our 0 is for the time, and 1 to 3 are the space coordinates, which can be in any coordinate system. Okay, you can take any coordinate system, Cartesian, spherical, polar, and any other coordinate system you can think of. Okay, so once you see alpha, you see beta, you see gamma, you should know that you have this. But when you read some textbooks, they start from 1. So don't get confused. At times you can have 1 to 4. At times you can have 0 to 3. Okay? So we have that. So this equation is used to look at the motion of test particles in a gravitational field. Okay? So, what are test particles? What are test particles? We need to differentiate between test particles, photons, and this other one. I don't know how to pronounce it. How do you pronounce this? It's TACHYONS. Okay. At times, when we pronounce some of these words, you laugh. So, what are test particles? In the context of general relativity, test particles are just particles that have a rest mass. Okay? That have a rest mass. particles that have a rest mass. So I'm introducing another mass again. Initially, I talked of active, passive, inertial. Now I'm talking of rest mass. Okay? What about photons? Because we are going to look at motion of test particles, we are going to look at motion of photons. But this set of particles, we will not go into this set of particles. There are other theories that examine this type of particles. Okay? There are other theories that examine this type of particles. So what are photons? Okay, they are electromagnetic radiation. Okay. Do they have mass or not? Are you sure? Are you sure? Have you heard of wave-particle duality? You are saying they are electromagnetic radiation. So they can behave as a wave and they can behave as a particle. So they have mass. But their rest mass is approximately 0. It's negligible. Their rest mass is negligible. Okay? I hope it has not gone off. It's okay. So we'll look at this set of particles. Who has seen this before? Okay? You know, in special relativity, we have a limit a particle can move to. What is that limit? What is the limit that you can accelerate a particle? You can accelerate a particle to what speed? The speed of light is the maximum in special relativity. A particle cannot move beyond the speed of light. Okay? But these are some particles that move beyond that speed. They move beyond the speed of light. Okay? They move beyond the speed of light. So, and that goes beyond our theory. There are other theories that we can use to explain that. Okay? So this equation, how many components do you expect this equation to have? Can we agree that this is a second order differential equation? Let's agree. Do we agree that this is a second order differential equation? Yes. Why? Okay. Because of this. And if you look at this will have how many components? 4. So in essence, we have 4 equations here. We have the first equation when this is 0. Okay. The X meter. This is the first equation. This is 0. And then the second equation will be when this is 1. The third equation will be when it is 2 and 3. Okay? So if we were working, let's say, in spherical polar coordinates, Then our 0 will be this. Our 1 will be r. Our 2 will be theta. Our 3 will be phi. Okay? So the first equation will be our time equation. Our second equation will be our radial equation. Our third equation will be our polar equation. And the fourth equation will be our azimuthal equation. So we're going to end up with 4 equations. But we have one funny guy here. This is what we call coefficients of affine connection. We call these coefficients of affine connection or affine connection coefficients. Okay? And it has how many components? 64. We have agreed. So it's going to have 64 components. Okay? It's going to have 64 components. And actually, this is defined from our metric tensor. From our metric tensor, we can get this other metric tensor. And then from there, we can get our coefficients of affine connection. Can get our coefficients of affine connection. The full expression is in the note. Let me see the next slide, please. Maybe it's there. Okay, it's not there. So actually, this one is defined in terms of G alpha gamma comma sigma plus G alpha sigma comma gamma minus G gamma sigma comma alpha. Okay, this is how you define the coefficients of affine connection. This comma represents differentiation with respect to this index. Differentiation with respect to this index. It represents that. So you see, it is defined in terms of this. And to move from this to this, we use what we call the quotient rule. Okay, which states that okay, I think I need to use a different okay. Okay, so this is our quotient rule. So if you have this is the Kronecker delta function, okay, which takes either 0 or 1, okay, depending on whether this is equal to that. So if this is equal to that, it takes 1. If this is different from that, it takes 0. Okay, so if we have this, remember I told you that once we have this, we are good to go. So if you have this, you can easily get this using this relationship, because the right hand side is just 0 and 1. So from this you get this. Then from once you have this, you can now get this. You can now get this. But the most interesting thing is that most of them will be 0. Most of the 64 will be 0. You might end up having just 5, 10 that are non-zero. Okay? So don't be afraid that you handle 64 that you handle 64 coefficients. Most of them will end up to be 0. Okay? And then this is actually false. Okay, this is false. Various components of force. Okay, various components of force. And tau is what we call the proper time. A proper time. Okay, tau is actually different from t, the coordinate time. T is the coordinate time, tau is the proper time. You can remember your special relativity. Okay, so this is all what we need to get the equations of motion of test particles. So if we have a star and we have a particle moving towards that star, we can be able to determine the way the particle will move using this equation. Okay? You can be able to determine the way the particle will move using this equation. So that is the equation we are going to use. And then the second equation is our field equations. Okay? Yes.
How do we extend now the equation of motion of the test particle
To
Lagrangian?
okay, the Lagrangian equation. We'll get to that. We'll get to that. Yes. Okay, if there's a collision between two electrons. I don't think so. I don't think so, Prof.
From the conical delta, you can see what you can say, okay, maybe when they come closer that the indices are the same, they just give you one to extract the equation you want. Most times, there's what we call collisionless atmosphere, and that is where these advent coefficients or characteristics get. They are there in space, but they don't have enough force to attract each other to the point that they will collide. Collisionless.
Are you satisfied? Any other question? Any other question? Okay, then our field equations, our gravitational field equations look like this. Our gravitational field equations look like this. G alpha beta is the same as 8 pi G over C to the power 4 T alpha beta. Actually, there are some physicists that still argue the authenticity of general relativity to date. Okay? And they base their arguments on this field equation. We had defined G earlier, okay, as a universal gravitational constant. Okay? So their argument is that this G is a dynamical quantity. So how come you take a dynamical quantity and feed it in a geometrical theory? Okay? How comes? So they still argue that. Even our lead prof, he also had, lead professor Owusu, he also had that, he had a double mind about general relativity. Okay? So you, in the course of reading, you might come across such arguments being put forward on the authenticity of general relativity and so on and so forth. So this is how the field equations look like. So how many field equations do we expect? How many field equations do you expect? How many? There are 16. Who has seen why there are 16? Who has seen why there are 16? Because we are dealing with tensors of rank 2. This is a tensor of rank 2. This is another tensor of rank 2. Okay? And this tensor is what we call the Einstein tensor. It's the Einstein tensor. This is how it's defined. It's called the Einstein tensor. And this our R is what we call the Ricci tensor. Okay? It's what we call the Ricci tensor. And this Ricci tensor is gotten from the Riemann-Christoffel tensor that I mentioned to you earlier. Okay, this is a tensor of rank 4. This is the Riemann-Christoffel tensor. And if you want to lower the rank of a tensor, you equate two indices. You see, this index is the same as this one. So it will give you a tensor of rank 2 less than the previous tensor. So this is a tensor of rank 4. And this is a tensor of rank 2. Okay, so you get this tensor from this. Then the question there is, where do you get this one from? Where do you get this one from? You are going to get this one from here. So you can see the root. We started from here. We went to this. We went to this. We are now going to this. And then from there we are going to this. And then we are ending here. Can you see how smooth our journey has been? There's no galloping on the way. It's a very smooth journey. Started from here and so on. So you cannot get to this without passing through this. You can't have the Einstein tensor without going through all of this. There are no shortcuts. There are no shortcuts. So we'll go through them bit by bit. Okay? And then there is this constant too, which we call the curvature scalar. We call this the curvature scalar. It's also gotten from this by again equating indices. Once you equate indices, you get this. And then on the right hand side, we have this tensor, which we call the stress tensor. And again, when you come to the stress tensor, you also see mass density. And that's another argument again. How can you define a tensor in terms of a dynamical quantity? Okay, and then you have pressure. P0 is what we call the proper pressure. And rho 0 is what we call the proper density. C is just the speed of light. Okay, so we have that. So the other things are just, these are just constants. They are just constants. They are just constants. Any questions so far? Any questions so far? Any questions so far? Okay, so we'll end here for now. Where is my flash? Yes, sir.
Introducing a dynamical, because Prof. till he went to his grave, never agreed. Why are you picking a dynamical? I thought you asked that question. Compliments and introducing it to a geometry, because he was always telling me about this G. Always. He said, why is this G here? So do you have an answer to that?
Let me just come in.
Sorry.
First of all, when you look at where you are working from, you are talking about spherical geometry.
Sometimes you know,
And your work is actually applicable to stars. That's where it comes in. Because you're now moving from the Kepler's law that is introduced under Newtonian into spherical geometry.
Thank you, Prof. So, and the issue is, you know, in theory, as Prof has said, you always look at where you are coming from and where you are heading to. And if you are able to come up with something that can be better than and neater than what was previously there, okay, good and fine.
Anyway, you see one other thing that because when we go to the solar atmosphere, densities are there, pressures are there, within which there will be a collapse. And then one of the issues of bringing a dynamical variable in a geometrical system is to avoid that collapse.
okay. So we can say that these dynamical quantities are ubiquitous. We cannot do without
You
them.
can do without, yes.
So that then you see why he says that Newton's laws are more universal. Because Professor also goes ahead to use Newton's laws to do almost everything.
Yeah, that is it. That
And
is
they
it.
have a way of reducing back, but most of this cannot be reduced back to the principle of equivalence. You can't go back with this, but the Newton's law can take you back. So Professor also was trying to generalize that he can use the dynamical equations to do whatever Einstein did, and actually he did that. You know.
Is it like,
we'll come to that.
you are talking about channels, and you are talking about channels you are not working. Channels are just fictitious variable particles that are introduced to evade the speed of light. And you see, they are mostly using scientific fictions. They are not experimentally achievable. But they are also trying to say something that will be higher, faster than the speed of light.
That is it.
Thank you, Prof. I think we are in for a lot. Thank you, sir.